Okay, I'm going to get started. My presentation is on do you feel the need for speed? And it's really my top 5 tuning tips for SQL Server. My name is Janis Griffin. I'm a senior systems consultant at Quest, new at Quest. I've just been there a year now. Actually, I was here at PASS last year speaking for Quest after being hired just 2 days into it. So it was kind of fun. Just if you all could silence your phones, a little bit of housekeeping. If you download my slides, you can see all of these resources that you can do here at PASS Summit this week. And a little bit about myself. I've been a long-time DBA, over 30 years of DBA work. I started out with Oracle version 3. Actually did Sybase, which is now SAP ASE, which soon became SQL Server 7. And I've been working with those and MySQL. Those are my 4 strengths, I guess, as database types that I've worked in, although I've actually worked with many other database types throughout my career. I had my own consulting firm for 5 years and specialized in performance tuning, and that's what I do at Quest. I work with our customers, our prospective customers, looking at their databases and giving them some ideas of how to improve that performance. Please evaluate my session. I guess if you enter it in by 5 p.m. Friday, you can win a prize. But I like your feedback, so please be kind, but also let me know how I'm doing. Okay, I'm going to get started here. And just before I get started, I'd like to know my audience. How many people are DBAs? Okay, developers? Do about anything, that's what I call myself. Okay. What versions are you on? Anybody on 2000 still? We got, poor one soul always. How about 2005? Okay, a few. 2008? Okay. 2012? Okay, how about 2014? Okay, 16? Oh, good. More hands coming up on there. 17? Anybody looking at 19? Good. Yeah, 19's kind of fun. They've added a lot of little bug fixes and little niceties in it. Okay, the agenda we're going to talk about today is challenges of tuning. We're going to talk about my top 5 tuning tips, and then I'm going to work through several case studies as we go through. So the challenges of tuning, let's face it, SQL tuning is hard. A lot of times it's just trying to figure out who should tune. Is it the DBA? He's a production guy. He's keeping the lights on. He doesn't know the code, but you think he should tune it? Or is it the developer who doesn't get access to production, but he's expected that his code to work? So trying to figure that out is even hard. And then finding the SQL to tune, what to focus on, is hard. There's thousands of SQL statements in a database running. It could be millions, actually, each one unique to its own tuning problem. And so you have to pick the right SQL to tune. How many of you have ever tuned something and nobody notices? Yeah, chances are you're not tuning the right thing. You're not looking at the right query. Tuning requires expertise in many areas. You need to know how to read an execution plan. And you need to be able to interpret which data access path is the best. Do you do nested loops? Do you do hash joins? You got to know join methods and which one's the best for your query. You also need to be able to write good SQL. Because a lot of times, let's face it, you might have to rewrite that query in order to get it to run more efficiently. I really believe you need to know the business aspect of the SQL that's running. Who's using it? What's its purpose? Who's consuming it? And how often does it run? That type of thing. I can't tell you how many developers I've seen put in sloppy code in the database, in production, thinking it's going to be run once a week, only be run a million times a day. That brings down a database like no other. I actually worked years ago, worked at a manufacturing plant, and I worked in accounting, taking care of the finance database. And every month end, basically, the database just tanked. I had a line out my door complaining about it's slow. So I started looking around, and I found out that this accounting clerk was running these monthly reports that some of them were taking 8 hours. There was even one running over 24 hours. It was taking so long, and just bringing down the system. And when I finally went to her and asked what she was doing, well, she inherited that job. She was told to run these reports and file them. Nobody was looking at it. Those reports could just be shut off. That was the easiest tuning I've ever done. So, you know, it's smart to know the business reason why they are running that SQL. Tuning takes time. There's a large number of SQL statements. There's no cookie cutter approach. You can't apply the same problem solving to each SQL statement because each one's unique usually. It's considered low priority in some companies. I worked for a network company years ago that they just wanted to throw hardware, just throw hardware at it. It's going to fix it. But I tell you, a poorly tuned query will consume all the hardware you eventually give it. It might free you up a little while, but it's going to actually eat up any resource you give it. And then finally, tuning can be never ending, which is a good thing if you become good at it. You'll have people at your door going, tune this, will you? So here's my 5 tips. And I want you to realize that SQL tuning, there are 5-day courses just on SQL tuning alone. And so this 75 minutes is probably not going to make you an expert, but these are tips that you can actually use as building blocks for your own tuning toolbox. And hopefully you'll take them and start using them. So tip number 1, monitor wait time. Now, why would we monitor wait time? Well, if you're an end user waiting for a response from the database, you're wasting time, right? So if you monitor the wait time, and SQL Server helps you with this by looking at wait types and recording each step as that SQL request goes through the database, what it's waiting on and what it's using. And so it records that at each step. And if you, not just the total time record how much time that query is taking, but if you look at each step and each wait type that it's waiting on, you'll have great clues on how to tune it. If it's waiting on I/O, then you're going to reduce I/O, right? If it's using CPU, then you're going to look and see why is it using CPU? Is it doing too much reading? So wait types are really helpful. If you want to do wait time analysis, you basically go to the DMVs. Now we have the one guy that's 2000. DMVs came available, the dynamic management views became available in 2005 and up. But in 2000, you do have the sys processes table, so you still have this information in there that you can get. And basically, these are not all the dynamic management views, but they're real-time performance data that sits in memory. And they're not persisted on disk, but these are the specific views that you'd look at if you want to do wait time analysis. There's DM exec requests, which basically gives you the SQL handle, the plan handle, and the offset if it's a stored procedure. They'll give you the database ID, the user ID, and if it's a blocking session, it'll tell you it's blocking. And then notice the wait type is in there. And then you can join that with DM exec sessions to get the host name, the login name, the program name, the session ID. And you can actually join that with DM exec query stats to get logical writes and reads, as well as physical reads. And there's more information you can get to, as well as execution count. And then you can use these two tables, or two table value functions here, DM exec query plan and DM exec SQL text, to actually get the text and the graphical plan. So if you poll these, because like I said, it's not persisted on disk, so you have to poll this and store it off somewhere. But if you do that, you could quickly find out which SQLs are spending the most time in your database, and you'd have a great clues on how to tune them. It really makes a lot of sense. Problem with wait type in the DMVs, though, is it's not time-based. You can't look back to 3 to 5 a.m. This morning and say what happened, because it's actually data accumulated since the system started up. So it's not possible to see certain points in time. That's why you have to poll it at some interval and store it off. And you need to use other tools. For example, I've got the query. It's not rocket science that you can run on the next slide, and I'll go through that. But all you have to do is include timestamp and save it in a table. And you've got your little tool. Extended events came out in 2012, and they gather wait types and query results. but it's hard to see. You can't see trends over time. You can probably go back and see what happened during a time frame, but it's really difficult to use. Query Store came out in 2017. Do we have anybody using Query Store? Great. Yeah, why wouldn't you? It's what?
Didn't have in 16 also? Query Store came in 16?
I'm sorry?
The SQL 2016 Query Store.
Yeah, 2016 had Query Store, but not weight types. And I'm talking about weight types. So 2017 and above have weight types. And so does our products. Quest Foglight and Quest Spotlight actually has weight types too, and uses weight time analysis. Okay, to view types at the weight types at the session level, this would be the query you'd run. And notice here, I'm doing DM exec requests, and I'm looking at the real-time view at each session in SQL that it's waiting on. And it's got a status column, and you can see if it's suspended, it's waiting on a wait type. If it's running or runnable, it means the session is either on CPU or in the CPU queue. And if it's sleeping, it's idle. So as you can see here, my query, I don't know if I can kind of come in there and see this. Probably not very good. Here, let me get out of here. My query here is I'm selecting session ID, wait time, status, wait type, blocking session, text, the offset, the start offset and the end offset, and then the query plan. From DM exec requests, then I actually outer apply that with DM exec SQL text, pass it to SQL handle, and outer apply DM exec query plan, text query plan, and pass it the plan handle and the start and end offset. And notice what I'm not looking for. I'm not looking at background processes. There's nothing I can do with those. I'm not looking at any idle processes, and I'm not looking at myself. Because remember, I'm going to be polling. And if I'm polling at every second interval, I'm going to see myself. So I exclude myself. And so the results that you get from doing that, and if I hope I can zoom in here to kind of show you this. Let's see if I can get down there. For some reason, this is not working very good. So I can't zoom in, so unfortunately. But as you can see, I got session ID, my wait time. I've got 3 runnables, one actually running on CPU, and one suspended on async network I/O. It's doing some network access, probably feeding too much data to the client. So that gives me some clues on how things are working. You can also look at it at the instance level. Now, this is not all that important, except if you're having a problem right now. But if you're having a problem right now, the DMVs are since system startup. So what you can do is you can look at DMOS wait stats, and you can do this DBC SQL perf, and give it DMOS wait stats and clear it, and let it continue to capture right now. So you can see right now what it's waiting on the most. And then you exclude the idle waits, and you can see that most of my time in this one instance that I was monitoring actually spent 80% of it on a lock. So that's where I want to focus on fixing, right? That's what's easy to do with wait types. Now, I don't expect you to read this query, and I'm not going to go through it much. But I put it in for my slides so you can use it. It does work. It excludes all of the 2012. I haven't gone back and reworked it for 2019 or any of them, but it should get you close of all the idle. So it's excluding all the idle wait events, and then it's giving me the 95th percentile. And so you can see I'm waiting on SOS scheduler yield. That's 52% of my wait. Async network is 18 or 19% of my wait if I round up, followed by thread pool, and the rest is insignificant. So that gives me a feel for where my instance is doing all its work or waiting and spending all of its time. Now, it's not rocket science, this query. I just created a table, with a little select into RTA data, and I just select those columns from the DNV. And then I just run this every second, insert into RTA data this information. You don't have to do every second. It kind of depends on your workload and what you want to do. You can do every 10 seconds or whatever. But get it polling at some interval, and then you can go back and select from it. And so what I'm doing here is I'm going with doing a little CTA. I'm doing with RTA. Give me SQL text, wait time, and time in seconds. And I've got an inner join that's looking for SQL text, wait type, and count for seconds. And then I actually do another subselect and do text and count for total time. And then I select from that CTE, and I order by total time, time in seconds, and wait type. And so you can see the one that spent, and I did this for about 3 minutes. And actually 3 minutes I did it. But this guy actually spent almost 5 minutes in the database during that time with all of its different weighting. You can see it spent most of its time on CPU. That's what the null stands for. I/O completion, it spent 68 seconds of it. And async network I/O, it spent 2. So this one is my top SQL in my statement. And now I have a clue of what it's going to do, what I need to do with it. You know, it's doing I/O completion, so it's having some problems there, but it's heavy on CPU. Usually, SQL queries should not be heavy on CPU. If they are, they're probably thrashing memory by reading too much data. Look at your logical I/Os. That's my hint there. Here's just an example of extended events. In 2016, this doesn't have, it shows wait types in extended events. And as you can see here, I've actually grabbed the SQL text and the wait type, and then I actually ordered by the sum of the aggregation there. And so I/O completion is my biggest weight in this database. And that is the top SQL right there. In the query store, in 2017, they actually now store wait types. So I can get my top 10 queries weighting the most. And this query actually does this. I go into query store wait states, join that with query store plan, and join that with query store query. And then I go get the query store query text. And then I group by and just sum the milliseconds. And you can see my top weight here is this select total income, order times unit price. It's doing a little calculation. And it's been over an hour waiting on parallelism. Now, parallelism really isn't, it's more of a status. It really isn't a wait. It's just multiple processes are being used in order to complete this query. So it's expensive. Okay. So wait time analysis focuses on the SQL statements that are spending the most time in your database. And you can get great clues. For example, this one query here, which is actually going to be a case study that we're going to talk about, where it says select first name, last name, and I apologize that it's so tiny, but I don't know if I can zoom in. But you can see that it's the top SQL, meaning that it spent the most time. And so when I highlight over that, I can actually see the resource consumption and see what it did. Oops, sorry. And so you can see it spent most of the time on a network wait. In fact, this thing actually did logical reads of 2.2 million, and it executed about 5,000 times. Taking 25 milliseconds, 26 milliseconds each execution, so on average. Other wait time analysis benefits that you can get by doing this methodology is you can get baseline metrics. When I tune, I like to take baselines. What is it running now? How long does it take? And then I like to think in my mind what is going to be acceptable. And the reason why I do that is if you don't, you'll tune until the nth degree. I drove myself crazy years ago because I couldn't put it down. I just kept tuning, because trying to eke every little bit of performance out of it. And so it's good to have an end game. Just stop looking at it at some point. And also it's good to set expectations. If you've got a query that's taken days to run and they want it sub-second, you may have to set expectations that it might be a re-architect. You probably won't be able to tune that down to sub-second. But if it's running 10 minutes and you need it sub-second, you probably can do that. But don't do it to, no seconds. I mean, stop at some point. And then I always like to record logical reads for tuning comparisons to see that I'm improving it. And the reason why logical reads is because every query has to do at least one logical read. May not have to do a physical, maybe in cache, but it has to do at least one logical read. So if you can get the logical reads tuned down, you will basically improve the query. Okay, here's this query again. This actually came from a university. They were trying to get their billing out, and they couldn't. We went in there, and with wait time analysis, we found this was to be the top SQL running in the database. And they're selecting first name, last name, sign-up date from student, and they were joining that into registration, if you will, on student ID. And then they were joining that into class on class ID. And they were passing the class. For the purpose of this, I actually have where CNAME equals SQL tuning. And then they were looking for yesterday. Who signed up yesterday? So there's our sign up between begin date and the day before. And then our canceled, because registration had a cancel flag in it. They never deleted from the table. It was a historical table. So if the student dropped or canceled his class, they would just mark him with a Y, that he canceled. So we're looking at only new records, so canceled equals in. So you can see, I gathered my metrics. The response time was 26 milliseconds it was running, 2.2 million logical reads. It did about 5,000 executions. And then basically you can see the network weight. It was spending 81% of its time on async network I/O, probably feeding data to the client. That's usually what that weight is. It's important to collect all the weight type information for a query, because if you've got different weight types within the same query, sometimes tuning one will bring the other one down. Sometimes they won't even match, and you'll just have to tune them both. But it's important to look at all the weight types for the query that you're tuning. As I said earlier, weight types give great clues. And this is Quest. We have a little Weightopedia. If you Google Weightopedia Quest, you'll come up with a little kind of a neat interface to look up weight types, get clues on how to tune. And we actually have a product that's called Spotlight Cloud that we have a lot of customers, and we just actually take the performance data from them, so we'll tell you how popular that weight type is, how many people are experiencing that weight. So it's kind of interesting. This one is a common one. Other benefits is what happens if something changes. All of a sudden this query ran slower. Well, why? Well, as you can see here, execution plan changed. And I can see that somebody, when I look here, dropped an index. It was using table access by row ID. Now it's doing table access full. So that accounts for the increased time it was spent too. Other benefits is blockers and waiters. I can now see who's blocking and who's waiting. So you can actually see that within the DMVs. Okay, so we found our query via my first tip, wait time. Now what do we do with it? Well, let's review the execution plan. Management Studio gives you several ways to get an execution plan. You can get an estimated plan, which I never do. It can be wrong for many reasons, because it's not the real plan that it executed. And especially if you're copying code and running it in development, it can be totally wrong because the whole instance may not be configured the same. Actual execution plans have to execute the query. It can be dangerous in production, and actual plans can be wrong if you copy them and put them in test with a different environment. But that's how you set show plan XML for estimated execution, or you set statistics XML if you want to do actual execution. Now, when I'm tuning, I always set statistics IO on, and I always set statistics time on. And I always use the actual plan. Now, in previous versions, for the 2000 versions, you had to only use tracing, and profiler tracing, which you can do performance execution plan in 2000, and you do show plan XML in 2005 and above. Profiling is really hard to read, lots of data, And also, you have to know when the problem is going to occur, so you have to turn it on, right? You're not going to run Profiler all the time. It takes a hit, and so it's not very useful. What is really useful is DM exec query plan in 2005 and above. It's the cached execution plan. It's really the plan that executed in production. So that's where I spend most of my time getting that. Now, what you can do here is you can select from this table value function, DM exec query plan, and you pass it that binary raw. Now, you don't put ticks or quotes around that binary raw. If you do, you'll get a weird message. And it won't say, don't put ticks around it. It'll just be a strange message. But you just pass it that binary raw, and then basically it'll give you the XML, as you can click on, and it'll actually give you the graphical plan, which is kind of nice to quickly see. And so when you're polling that and putting that in the table, you'll have the plan that you can see that it actually ran. So once you get the execution plan, what do you do with it? Well, examine for expensive operators. I look at the high-cost steps. Look at CPU, I/O cost. I look at row counts for each step. You know, full table scans and cluster index scans specifically draw my attention. Not that they're always bad, but I want to make sure they're warranted. If I'm reading millions of rows by doing a cluster index scan and only returning to my result set 1 or 2, that's an inefficient query. So I really want to make sure it's warranted. If I want to return millions of rows back to my end user, yeah, full table scan or clustered index scan is the way to go, but not if you're getting very specific data. I reviewed the predicate information. You know, understand how the predicates are being, the parameters are being interpreted. Are there implicit conversions? Because they're expensive. They take CPU power, and in fact, I think I have a link from Armor DBA. He writes all about implicit conversions in this deck, you know, and how horrible they are. So be sure you're checking the data types. And then I also believe that you should know which step to filter, the filtering predicate is applied. I always like filtering to happen earlier than later. I mean, if you think about it, say you've got 2-3 million rows, tables, and you're joining them. Do you want it to join all those 6 million rows and then throw out all the ones but you want? No, you want to filter up front. Filter first, and then build upon the select clause with the rest of the query. And then review join methods. Nested loop joins is usually good for smaller data sets or big tables with lookups or master tables. So that's nested loops. That's where you should be using, not hash joins. Hash match joins are useful for very large data sets, 2 huge tables. And then merge joins are also good for larger data sets. As you can see here, you know, I look at the clustered index scan. You can see how many rows it is on the cost, and you can see actual versus estimated number of rows. Okay, so here is another case study that we're going to be talking about. And this happens to be on AdventureWorks, and it's the customer, it's getting customer information out of sales order header. It joins into customer and customer ID, and then it joins into order detail on sales order header order ID, and then sales order detail joins into product on product ID, okay? In this query, we're looking for online, where online order flag is equal to 1, meaning it's online orders only. We're looking where last name like C%, product name like mountain %42, and product ID like 9%. Like I said, I always like to turn on statistics I/O. And I usually clear the cache each time I run it too, so I have a clean system to tune. And you see order detail, we actually read 75,492 records. And order header, we actually read 29,876. So there are my logical reads. And when I look at the execution plan, I can see that it's doing a clustered index scan on customer, So it's doing a full table scan, if you will, because that's what a clustered index scan does, is reads the full table. And then it joins into person with an index seek. And you can always tell with the graphical execution plan how much data is being returned. You see how wide this one is? There's a lot of data being returned to that step. If it's thin, it's a very small amount of data. So I first do that, and I send it to hash match to get a result set. And then at the same time, I do a clustered index scan on order header. And I push that into another hash match join. Okay. And then I finally go get order detail. I do a clustered index scan. And that result set, along with the rest of it, is thrown into a merge join. And then at the same time, I actually do a key lookup into product. And I'm using alternate key product name to index to do an index seek into nested loops. And then I finally do a hash match join on the final result sets to get my select. Now you can see that Management Studio says, you're missing an index here. You should add a covering index on online order flag. And oh, by the way, put all these columns as covering. Now, covering index is really quite efficient because when you put include, it actually sits at the leaf of the B tree. So it actually sits at the bottom leaf. So it doesn't really have to change ever. It doesn't get updated like the indexes and the actual navigation. So it doesn't fragment. So covered indexes are quite efficient in that now, if I add that covered index, I wouldn't have to go back to order table, right? I'd have to just hit the index, get all my information out of there. So I at least reduce it by half the IOs. Okay? So that's the execution plan. Now what do we do? Well, let's learn about the objects in my execution plan. I really believe you got to take your time and understand what the tables are made up of, how big they are, what's the selectivity. First off, is it a table or is it a view or a table value function? Management Studio can help you. If you just hover over the table, it'll tell you whether it's a view or not. I think it's important you know where it physically resides, you know the keys and the constraints, and you know the size, selectivity, data types of the columns. And you can do this quite simple with SSIS. There's a data profile task, and you go out there in your menu, and you can actually put in your tables of the queries that you're doing, and it'll actually spit out the null ratio. It'll give you all the statistics about the different columns. So it's really easy to do with SQL Server. Other databases don't give you this nice little utility to do that. And I also think it's important that you know what your statistics gathering is doing. Do you have auto on? If you do, it may not be enough. You may have to gather more statistics. So you may want to think about that. If you're finding, if you're having to rebuild indexes or your statistics are out of date, the optimizer is not going to give you good execution plans. You need to review table, column information. Get all the row counts, review the selected columns. Try not to use star. How many people use third-party SQL, like Hibernate or any of those to develop with? Anybody? Well, they write crappy SQL. So they try to select everything and give it to the client to filter it out, and it just kind of actually ruins the whole relational database technology that it's there for. So you look for performance degraders. Try not to use case, cast, or convert. Try to avoid subqueries and make sure everything's indexed. Make sure it's sargeable. And then examine the where and join clauses. Bad signs is there are no filters. You're just selecting everything. Or, like this one little SQL statement here, I'm just selecting distinct sales order ID, carrier tracking number, product ID, order quantity, line total, and modified date from sales order detail. No where clause. There's nothing I could do as a DBA to tune it. Now, a quick way to actually get this information, the sizes of row counts, is you can actually select name, rows, and type from sysobjects and join that with syspartitions. And you join that on object ID. and I'm looking for a table function, user table or view, and I bring back all of the statistics that are on these tables. So you can see my order detail is about 5 million rows. My order header is 1.2 million. The rest are, rather small. But those are my two large tables. Okay, we also want to review indexes. Get the index definitions, know the order, and their selectivity. SQL Server needs the left leading column. If it's a multi-column and you don't give it the left leading, it won't use that index. You've just effectively turned that off. So make sure you always have the left leading column in the where clause if you want it to use that index. Also, think about ERDs. Maybe, it's easy enough in Management Studio just to build yourself a quick ERD and see the relationships. I've seen developers not understand the relationships. They may get the right answer with their query, but they leave a significant part of the query out. And it's the relationships they forget about. And that gives the optimizer such a better way to write a query. So, I've also seen a lot of developers leave off constraints entirely because they think it slows it down. And that's not, good reasoning for that as well. So just remember, keys and constraints can help build better execution plans. Now this is my little university query. You can see registration has an index on student, class ID, and sign-up date. It also has a foreign key from class into registration on class ID, and another primary key on student, and with a foreign key into registration on student ID. It's important to know that the optimizer can use the index. And if you're building functions around the column name, it's going to turn off the index. So you might want to consider rewriting it and put the function on the other side, maybe on the parameter that you're passing. And also look for implicit conversion. Here is an implicit conversion in one of our case studies where I'm doing product name and like mountain. And look, my convert implicit, varchar 12, and it was an integer. So it's doing an implicit conversion. Very expensive. And then finally, you can always use SP help index to get the different indexes on a table and see the different columns and everything. And I also think it's important that you know index rebuild schedules, because if you're rebuilding your indexes on a nightly basis, you may experience it running great in the morning, and it fragments by the end of the day, and performance wanes that way. So it's a good idea to know when you're rebuilding your indexes. Okay, so let's review. First 3 tips. Monitor wait time. Look at the wait types. Second one is get the execution plan and review it. And the third one is understand all the objects in the query. Now my 4th step is find the driving table. And you really need to know the size of the actual data sets of each step and look at what they're actually touching. And you also need to understand the join criteria. If it's a right or left or outer join, it's going to make a difference on how much data it's going to return. And you also need to know the filtering predicates and when each filtering predicate needs to be applied. Because like I said, you want to filter earlier rather than later. And then finally, you want to compare the final result set with the rows examined. You want to drive the query with the table that returns the least amount of data first to reduce logical reads. How do we do that? We're going to go through this case study now. And this is at university. I just listed it here again. And this is a 10-minute time slice that I watched it run. And it actually did 3 million logical reads. It was taking approximately 2 seconds to run each execution, most of it waiting on async networks I/O. We found it because it was the top weight in my database. So let's look at the execution plan. The execution plan is doing a table scan in class, and it's also doing a clustered index scan in registration. And it's actually a high-cost step. It's 60%. And then it actually feeds that to a hash mash join, and then it does a clustered index seek of student and throws that into nested loops. Again, it's saying you need to add an index. And it wants me to put it on canceled and sign up date. Do I do it? How many would just blindly go out and add that index? Good. Right answer. Nobody raised their hands. Yeah, don't do it. What I like to do is I like to review logical I/O. So I get my I/O, and there's really not that much. Student did 38 reads. I did a work file for whatever reason, and a work table. And registration ran 400 logical reads, and class read 13. So I review the tables and indexes, and I see, class doesn't have an index. Remember, we found that in our wait time. The change control said an index was dropped, and it planned and changed. So there was no index on class ID. But there was an index on student ID, class ID, and sign-up date and registration, and an index on student ID and student. And you can see 79,800 for registration, 10,000 for student, and I've had about 1,000 classes in the class table. So how do we know where to drive that table? And I like SQL diagramming. I don't know if anybody has ever done SQL diagramming in here. It's an oldie but goodie book that I don't know Dan Tao, but it is a good book. And it's actually, I've proven it through all the different database types. This methodology works. And so if you want to learn more about it, you can go download the book, the link's there. But really all it is just finding the best filter. And the way he says to do it is you start with your detail table and you draw an upside down tree. So our detail table was registration, and I draw links or these arrows out to the lookup tables. So I had 2 lookup tables, class and student. And then these numbers on the side of these arrows are basically, I'm saying for every one student, I have probably about 5 registration records. And for every one class, I have about 30 registration records. Now this was a university, but this is my data set. I went and actually got the ratio. And so that's the way it worked out. So with the tables, I should never have to join for any one student or any one class more than 150 records. Okay? Then I go look at the filters. And you can see I had several filters. I had one on registration where canceled equals in and sign up date equals yesterday, if you will. And out of that, I got 4,344 records back out of the 79,800. And so 5% of registration would have to be read. That's my filter on registration. I also had another filter on class, where name equals SQL tuning. And there were 2 records, probably different levels of tuning. And so 0.2% is that filter. 0.2% of class is going to be read. Which is the better filter? Class, right? So I want to drive this query by class. So as we go in here, let's first fix the problem of the dropped index. So I created a cluster index, class PK, on class ID, but our filter was on class name. So I created a non-clustered index on class name and called it class name IDX. And so then I ran it, and you can see class reduced the reads from 13 to 2, registration, no change, and student, no change. Why is the clustered primary key doing a scan? Well, if you look, what's my index on registration? It's sign up date, class ID, or student ID, class ID, and sign up date. It can't use class ID because it has to look at student first. So what we need to do is add an index on registration. And we can actually use our wait time to see if we improved it. It didn't improve much, hardly any. You can see the blue is what it's doing now versus what it did with the gray. It spent more time in the database with the gray, but actually did a little more executions too. Well, let's go add an index on registration. So I give it class ID. And I give it a non-clustered index there. And now you can see I'm doing an index seek on registration. I get that from 400 logical reads down to 63. And I still got this clustered lookup though. What's the deal with that? So this is a clustered lookup in registration that I want to go add a covering, so they don't even have to go back to registration. So I create a non-clustered regalt index again, and I exclude all the columns from registration, so I don't have to make an extra I/O to the table. So class ID, sign up date, and canceled, and I put them in that order because the most specific to the least specific. Canceled was just to value a field. Okay, so what did we get it down from the original 400 IOs to 6 IOs? So we tuned it. And 4 times faster, 3 times the throughput. You can just see when it popped. So, yeah. Now I'm done with that one. Okay, another case study is this one that you'd seen earlier with the customer query. And we're going into sales order and customer person, order detail, and product. And I chose this one just because it's a little more meaty for the diagramming example. And you can see my joins and my filtering predicates here. You can get my baseline. So I found this because it was the top query running in my database. And you can see my metrics here that I got. This was doing 92 million reads. It had done about 400,000 rows, and it executed 439 times. So, it was doing an awful lot of reads. And you can see most of its time is being spent on CPU. And that's what logical reads do to you and your system. If you're doing logical reads, it's going to thrash memory, and it's going to take up CPU. Okay, so here's the execution plan. And I know you can't, I don't think I can zoom in here to do it any justice, but you can see it's doing an index scan on customer. Yeah, I just can't get in there. I can't get down there. It's also doing an index scan on sales order detail and a clustered index seek on sales order header. And you can see it's doing 126,821 logical reads on sales order header, and it's doing 79,270 reads, logical reads on sales order detail. Okay. And it's also doing cluster scan on customer. Okay, so let's go look at the indexes and the sizes of the tables. And we can see that there's 7 million rows in order detail, almost 8 million rows, and then 2 million rows in sales order header. And the other tables are relatively small. There is alternate key on product name. There's also a primary key on product ID, which, it was using product name. I don't know why it isn't using product ID. And then we also have last name, first name index, which, if you remember our query, we're looking where last name like C. And we're actually, sales order detail has order header and order detail indexed. Let's diagram it out. How are we going to drive it? Well, I've got the join criteria here. And you can see my order detail table has a lookup in order header and a lookup in product. And then order header has a lookup in customer and a lookup in person. Customer has a lookup in person. And so that is the way it maps out. Now I can figure out the join, and this is how I figure out the join selectivity. But really, if you just ensure all your join columns are indexed, you don't have to do the math. It'll do the right thing. So just make sure all your join columns have an index on them, and it'll do the right thing. It's more the filtering criteria that is important. And so here we had one filter on online order flag, and you can see the majority of that is online. So 88% of order header table would have been read with that filter. So that's not a really good filter. On person, with last name like C, there was, it rounds up to 7% of person would have been read. And then finally product, where name like mountain and product ID like 9%, 3 came back. was really, it rounded up to 0.6%. So my best filter is product, right? I want to drive this query by product. Well, first thing you got to ask yourself, why isn't the clustered primary key being used? That would be the best choice. Why is it doing this using AK product name? And I do have an index on last name, so I don't have to worry about that. But it's doing a key lookup, and it's using AK product name. So when we look at that, there's my implicit conversion. It's taking that product, like 9%, seeing that it's a varchar, and so it's converting it because actually product ID is an integer. So it can't use the primary key. So my last tip, engineer out the stupid. And this is my favorite step because I always find myself here. But usually there's silly things you do when you're trying to get code out to production, and you're just trying to get it to run one thing, and there's silly things you do. So you look for performance inhibitors. Look for cursor or row-by-row processing. Relational databases love set processing. They don't work good row by row. Look for parallel processing. Look at your max DOP. If you've got a degree of parallelism default, it's going to see any query as expensive and try to parallelize it. So it's going to take up CPU and more processing than you really want it to. Look for hard-coded hints. Not that hints are all that bad, but they can be put there from years ago, and that data changes, and then they no longer work. Nested views, especially against linked servers, try to avoid that. See about replicating the data or something a little quicker instead of going over linked servers. Look out for abuse of wildcards and no where clauses. And like I said, third-party SQL generators such as Hibernate or LinkQ or any of these will actually write you some bad code if you let it. And then, I can't say it enough, implicit data conversions. They will kill you. And there's, like I said, this Armor DBA, he actually gave me his paper out there. He blogs about it, and if you want more information, you can click on that. And then also make sure your columns are indexed. I just seen one come in from a customer not too long ago that was select, and there were columns names where upper, and they put upper around the column name, and then they passed in a literal. And it's like, it seems like they could have fixed the data, the underlying data, instead of doing that. Well, I'm going to fix my stupid. So I'm going to try to fix this stupid first. And when I got to looking at product ID, yes, it was an integer, and it had values 1 through 99. I was getting the wrong answer before because I wanted anything greater than 900, equal to or greater than. So I was actually getting the wrong answer with the first query. As you can see, there's no implicit conversion now, and it's doing the right thing. It's using my clustered index seek, going right to that product ID. And then basically, it's still doing that scan on sales order ID. I still have some work to do, but I am driving by product now. So you can change indexes to reduce I/O, and there's a lot of different indexes that you can use in SQL Server. I don't cover them all in this class, but I do want to talk about these three. Like I said, the covering index saves a trip back to the table. There's also the filtered index, and the filtered index is really nice, especially if you've got very large tables, and you don't want a large index, because you could filter it on a certain value. So in my filtered index, the majority of my data was online order flag equals 1. But if I was looking for 0, I might want to just put that index on the 0 and have a very small index. What's nice about filters index is it doesn't take so much to maintain them, because if it isn't a 0 or a 1 order flag, it doesn't have to update the index when you're actually manipulating the data. Okay, or you can have a combination of both the covering and filtered. So here's an example of I've used all the columns in sales order header and included them, and I'm also just looking for where order flag is 1. So that index is much smaller, much more compact than holding the whole table. So let's add a covering index to this. And I add a covering index, and you can see index seek now in sales order order detail. And it's actually driving by product and sales order detail, does nested loops instead of hash joins, and then it picks up sales order header, and then does nested loops. And we've still got a clustered scan here on customer, and then we do a hash match, and then we go into person. It's actually suggesting we put another, this index is what I created on product ID, and I added order ID and order quantity. So we reduced the logical reads from 79,000 to 116. We're still doing 126,821 logical reads in sales order header, but we got this down to 116 logical reads. So then what do? Well, rerun the query, make small changes, consider adjusting the indexes some more if you want to. Run, check runtime details, compare the results with the baseline. I use logical reads. I think that's the best key measurement. And then, did you improve it? If you didn't, then rinse and repeat. Still high cost, because we got now a header that's high in cost, 90%. So what do I do with that? Well, let's add a covering index on header. So I do this non-clustered covering index on online order flag. I add order ID, order date, customer ID, and subtotal. And I get 128,000 logical reads down to 6,798 and 116 logical reads in sales order detail. So I improved it, I think. So you want to monitor your tuning results. Monitor the improvement. Be able, to prove that you've made a difference. You want to brag about yourself, because I'll tell you, no one else will. Compare the final measurements with the initial readings. And tell your manager you're doing something. You're saving them money. Monitor for the next tuning opportunity. Tuning is going to come back 10 to 1. If it's a popular query and the data is growing at such a pace, you're going to see that query again. And you probably have to redo your tuning efforts. But there's always room for improvement, and you make sure your tuning makes a difference. And so, did we improve it? Well, okay. We're all on CBO at the beginning. Now we've got a little more other things. Our response time was 1 and 15 seconds. We got it down to 38 milliseconds. Executions before were 439. It actually went up to 629 in the same time period. Logical reads, 92 million, down to 4.5 million. And throughput was 1.5 times greater. So we did improve it. And, so there is reason for my next raise, right? Okay. Final case study. I suppose I should see what time it is. Okay, we got time. It's on Department of Transportation. You can go out to DOT and download every flight for every year since I don't know how long. Probably back till the 1900s, I don't know. I downloaded it 2015. It's every flight, everywhere in the United States. And it's a star schema, so if you've never played with star schema, it's kind of fun to download and play with. And basically, I thought, well, it'd be interesting to see what cities and what days are popular to fly to. And so I created this procedure where I get city day flights. I pass a begin date, end date. I give it the city and the day of week. And then I go and actually query this schema. And I've got the actually description of the tables on the next slide. But I select carrier. The description is carrier name, the flight date, the flight number, the tail number, the originating airport, and the destination airport, and the originating city and the destination city, as well as day of week. And I join this, and this is my fact table, T on time, 2015. And I join it to a bunch of lookup tables. Unique carrier, airport is twice because I'm getting originating and destination. And same way with city market, I'm getting original and destination, and then the day of week. And I'm just passing in the parameters I want for that. Now here is what it looks like when you actually get it into a database. It's actually Excel spreadsheets is how you download it. So it was not fun to do all that, but because I think you download each month is what you had to do. But you see the fact table, and then you've got all these lookup tables here. It was a query spending the most time in the database. It's my top query again. It's spending most of its time on other weight, which actually it threw it into parallelism, because I had on default degree of parallelism 0, and it saw this as way too expensive, so it's just going to go nuts with it. As you can see here, this already did 12 million, almost 13 million logical reads. It was taking almost 16 seconds on average each each execution, and it only did 123 executions during this time frame. When you have a CX packet weight, like I said, it's a status. It's not necessarily a problem, but it is good to know what those parallel processes are waiting on, because that's going to give you a way to tune. So if you run this query and go look at DMOS waiting task, and you select from the session ID where from DM exec requests where wait type equals CX packet, you can see all the things that it's waiting on. And you can see all my CX packet, but actually it was actually waiting on a latch. And of course, what's that latch mean? Well, this is a good article by Paul Randall, but access methods data set parent points to max degree of parallel setting. And so I had the default unlimited. So consequently, the execution plan was pages and pages long of parallelism, table scans, parallelism, bitmaps, and it got so I couldn't even read it. You can see how tiny it is. So I just thought, okay, we got to go look at things. So let's go look at the table and column information. And I'm looking at the size, and you see that T on time is about 6 million rows. All the others are insignificant. But notice all of my index IDs here they're all heap. They're all heap. They're not clustered indexes at all. Because what I did was I loaded in the Excel spreadsheets and ran with it, when I should have figured out that, yeah, there's got to be some keys available. So I created clustered indexes on all of them. It took me a little while to find the uniqueness on them, but I created unique clustered indexes. And then I went and turned off parallelism, because I didn't want it to parallelize, because it was just taking up too many processes. And you can see now my index ID is 1, which means it's a clustered index. So let's go find the driving table. And since this is a star schema, there was 3 filters on it. And you can see we had on time where flight date between, if you will, some dates. And we had quite a few records being returned by that. In fact, 8% of on time would have been read, which is a 6 million row table. So that was quite a bit of rows that we were going to read. We also had another filter on description, which is the city, on city market. And basically, 0.017% came back. So rounded up 0.02% of that table is going to be read. And that's a pretty small table. And then, of course, we had day of week, which was really only 8 records, but 13% of that was going to be read. So we're going to drive it by city market. So let's go look at city market. But first, let's find out that, oh my gosh, we have an implicit conversion. Because when I put it in an Excel spreadsheet, date doesn't become date time, right? I have to tell it it's date time. And so it was converting it to date. And that was turning off that index. Or it was doing an implicit conversion. It was doing a clustered seek, but still I didn't like that it was doing that clustered conversion, or a convert implicit. So I fixed the stupid. I took flight date. Instead of a varchar 50, I made it date time. And so now we're doing it appropriately. So there is no implicit conversion. And then I created an index on L-City market ID description. So did we improve it? Yes, we did. I mean, we got down, I don't know, I can't remember how many logical reads, but we got it down to 37 million. I think it was like 90-some million before. And we actually bumped up, instead of 123 executions, same time frame, we actually executed 1,944 executions, returning a row count of almost 4 million. And most of it waiting, instead of CX packet, on async network I/O. So did we improve it? Yes, we did. Response time, it went from 16 seconds to 47 milliseconds, 8 times better in throughput. So in summary, there's a lot of challenges with query tuning. If you just remember these top 5 tips, they should take you a long way, though. Just remember, monitor wait time, review the execution plan, gather the object information, and find the driving table. And then always remember that last one. That trips you up every time as engineer. That's stupid. Okay, thank you.